All right, so let's get started. Hello, everyone. Good morning and good afternoon. Welcome to the ASA section on Statistical Learning and Data Science Monthly Webinar. My name is Boxiang Wang from the University of Iowa, and I will be your moderator. Today, it's my pleasure to introduce the speaker, Dr. Lihua Lei. Lihua Lei is assistant professor at Stanford Graduate School of Business and assistant professor of statistics by courtesy. He got his PhD in statistics at UC Berkeley and spent 3 years at Stanford Statistics as a postdoc. His research areas include causal inference, machine learning, AI-assisted inference, econometrics, experimental design, compound decision theory, multiple testing, network clustering, and stochastic optimization. Today's talk is on compound selection decisions, an almost sure approach. But as an audience, we are quite already sure that we will learn a lot from this talk. Professor Lei, over to you.
Thanks so much for the kind introduction, Boxiang. And I'm very happy to be here to present my recent work on compound selection decisions, an almost sure approach. So this joint work was an amazing team. Kevin Chen, Tim Sudijono, Liang Song, and Tian Xie. So this is a joint work with both economists and statisticians. And it's been really a great pleasure to work with this team. And I'm going to start by talking about compound selection decisions. And by the way, if there's any questions during the talk, feel free to unmute yourself and or feel free to put the questions into Q&A, and I will take the questions in the middle. And also, I will take questions in the end of the talk. Okay, so nowadays, well, the first example I want to talk about is the so-called experimentation program. So we know that A/B testing has been so popular over the past decade. And at this point, for a lot of big tech companies, they already have a big suite of A/B tests. And they're now running multiple A/B tests at the same time. So then as a manager, one of the questions that you need to answer is that instead of treating each A/B test as a separate test, what subset of the features should I ship? Because here, as a manager, we're thinking about whole experimentation program as a whole. So then we want to ship things that can benefit the revenue or any positive side of the business. So here, the question becomes to select revenue generating features to launch. So the second example is the so-called economic opportunity. So there's this very famous creating move to opportunity experiment where people are paying like low-income households to move to other neighborhoods and see what's the impact on their children's income. So this is what economists call intergenerational mobility. And one question for policymaker is that with all this noisy estimate of the economic mobility, suppose I'm willing to spend some budget moving the low-income households into some census tract or some regions, then which census tract shall we move them to? So again, this is a selection problem, and we want to select high mobility census tract. And the last example I want to touch upon here is related to employment discrimination. So in economics, there's something called resume correspondence experiment, where people send fake resumes to the companies and trying to detect employment discrimination. So here, let's say, suppose you have two groups. One has white sounding names, one has black sounding names, and all other things are kept comparable or equivalent. So then they want to look at what's the callback rate differential. So in this case, we want to select firms with high callback rates differential. So all three problems are related to selection. And also all three problems are compound in the sense that we have multiple things to select from. And each different thing are more or less comparable, but they're operated at a separate base. And because of this, now we can think about the overall welfare. So in this case, the overall welfare can be defined in this sum. And over the next couple slides, I will walk through that definition of each term here. So the first one is, here we have a sum, and we have multiple units to select from. So this is what we call compound, because we have multiple tasks or objects to work with. So in the case of experimentation program, this I indexed the A/B test. For economic opportunity, this I indexed the census tract. And for firm discrimination, this I-indexed firms. So this compound decision framework came from Herbert Robbins from 1951. So actually, Herbert published two papers, two famous papers in 1951. One is SGD, the other one is compound decision making. So both are super influential. And recently, in the economic literature, in the economic community, people are picking this up because they have found a lot of problems that share this feature. And the second thing is about mu I and ki. So here we assume that the mu I is the benefit and the ki is the cost. So mu I minus ki is the individual welfare. And throughout the talk, we're going to assume that mu I and ki are fixed. So they're not random parameters. So we're not going to impose a prior on it. And for the experimentation program, this mu I is what tech people call North Star metric, and ki is the guardrail metric. So for example, the North Star metric can be the revenue increasing, and the guardrail metric could be the loss of engagement. And then the economic opportunity, in that case, mu I is the lifetime income growth times the compliance rate, and ki is the front-loaded program cost. And for firm discrimination, mu I could be the loss in social welfare, and ki could be investigation cost. So in this case, you can see that by juxtaposing mu I and ki, we implicitly assume that they have the same units. So for example, for an experimentation program, we assume they both can be measured in dollars. So this is not always suitable. But for the purpose of this talk, I'm going to focus on the case where mu I and ki are comparable, and we can use mu I minus ki to measure the individual welfare or the net benefit. So then it comes to delta I. So here, delta I is either 0 or 1, which measures selection. So for experimentation program, this means whether we ship feature I. And for economic opportunity, it's whether we select census tract I to move low-income families to. And for firm discrimination, this is about whether to report firm I as engaging in discrimination. And for the purpose of this talk, we don't allow for randomized selection, because for this type of compound selection problems, it's pretty crucial to either select or not select. Having randomization could further boost the statistical property, but it will make the policy making a lot harder, because in practice, we're engaging in this dichotomized selection. So once we have the welfare, then we can try to maximize it. So if we were to know mu I and ki, then we would just select everyone that has the benefits outweigh the cost. So this is the oracle decision. But of course, in practice, we only get noisy measurement of mu I. And throughout the talk, for simplicity, we're going to assume that ki, the cost, is known. And handling unknown ki is not difficult. And it's partly already in this paper, and also partly in one of my other ongoing projects. So in the case of experimentation program, this mu I could be the incrementality estimate or treatment effect estimate from an A/B test. And for economic opportunity, this could be the measure of the upward mobility from the CMTO experiment. And for firm discrimination, this could be simply the difference in the callback rate in the resume correspondence experiment. So for this talk, I'm going to assume that this yi is normally distributed with an unknown mean mu I and known variance sigma I squared. And we assume that y1 through yn are independent. So of course, we can think about other settings. So I would say for this is really just a starting point of thinking about how to solve this problem. And later in this talk, I will mention a much more realistic case where this yi is obtained from some microdata. So for example, when you have the treatment effect estimate from experimentation program, then we actually get it from the individual data. So there, we're obtaining this yi as the average of micro or individual level data. So there, we can imagine that this Gaussianity can be approximately held. So then I will talk about results related to that. And also in the paper, we talk about a case where yi is Poisson. And in another paper, in a companion paper with Yan Chen from Duke, we also discussed the case where yi is binomial. So if time permits, I will have 2 slides talking about that. And also in another ongoing project, I'm thinking about the case where yi is normally distributed, but sigma I square is unknown. But for the purpose of this talk, I'm going to focus on the setting where we have a normally distributed measurement and sigma I square is known. Okay, so because we only have the noisy measurement, so we can't really get to the oracle decision. And also recall that the oracle decision involves mu I and ki. So even when ki is known, we still need to estimate mu I. But in this case, we're assuming that we have this non-negligible sigma I square, which doesn't go to 0. So in this case, we can't simply do plugging. And our goal here is to learn a statistical decision rule that could potentially depend on all data, y1 through yn, such that if you deploy this decision, then the average welfare over the randomness of data is on average high. So here we can consider many different selection rules. So the most common selection rule is the separable thresholding rule, where you compare yi, your noisy measurement, with the cost, and you select if it is above a certain multiplier times the standard deviation. So the standard one-sided p-value thresholding corresponds to setting C to be 1.64. And another commonly used rule is that imagine you're a Bayesian and you can impose a prior, and this will give you the posterior mean. So then if you truly believe in this prior, then the optimal decision would be just comparing this posterior mean with the cost and choose the ones whose net benefit is strictly positive. So in this case, well, maybe we don't truly believe this Bayesian or this prior. So then we can use empirical Bayes to estimate the prior. And we can also change the threshold from 0 to something else to just to gain more flexibility. So without loss of generality, we can consider conditional thresholding rule that looks like thresholding yi at some cutoff that can depend on y minus I, or everything but yi. So it turns out this without loss of generality can be derived by something called Carling-Rubin theorem, which shows that, well, for this particular problem with Gaussian measurement, we can, so only the conditional thresholding rules are invisible. So for the purpose of this work, we're going to focus on an even simpler set of rules, which is what we call parametric separable thresholding rules. And here, we're not going to use other yi's to learn this cutoff, but rather we're going to use all the side information, including sigma I, to learn a threshold for yi. So in this case, well, we are going to use this beta to parameterize this decision rule. And this, for simplicity, we are going to assume that this beta is a finite dimensional parameter. But in general, we can also handle some non-parametric classes like isotonic regression and things like that, although we didn't cover that in the paper. So for now, just think of beta as a finite dimensional parameter. And one criterion we impose on this decision rule is that we require this decision covers some baseline decision for some value of beta. So for example, if you're using p-value thresholding, then you want to include 1.64 or 1.96. So later on, when we optimize this welfare across beta, then at least we can guarantee to be better than baseline. So this is no harm principle that we impose in this work. So we want our learned policy to be always better than the status quo. So just to give you a few examples, here this decision rule can encode some practical constraints. So for example, for interpretability, maybe we can only use p-value thresholding. So like, for example, if you are presenting a case in a trial, in a court, then probably you can't really use fancier statistical methods if the judge doesn't understand it. So for those purposes, we want to use some simpler decision rules that look like beta times sigma I. And we know that if beta equals 1.96 or 1.64, that's the existing rule. So this does capture the status quo. And in other cases, suppose we do have the flexibility to choose whatever decision rule we want, then we could use Bayesian rule. And we can parameterize the prior using some beta. So in this case, we can design our decision as thresholding this posterior mean at 0. And so for monotone score class like Gaussian, you can show that the posterior mean is monotone in the posterior mean is monotone in yi. So this can be written as yi greater than or equal to some cutoff. And lastly, suppose you have some unstructured data. So then you can use AI or machine learning to turn them into a one-dimensional quantity, and then you can directly add it onto the p-value thresholding rule. So all that is to say that even though now we are using a finite dimensional parameter beta to parameterize this decision class, it's pretty flexible. It can both account for flexibility and also for practical constraints like interpretability. And this is the class of things we're going to work with in this work. So then in this paper, we developed an almost Stein's unbiased risk estimator or a sure star for the welfare. And what's interesting is that for this class of estimate or welfare, we find that the exact unbiasedness is not achievable in this case, but the bias can be made arbitrarily small. And also, this assured star estimator can work with any class of decision rules. And based off of our estimator, we established regret bound for bounded VC dimension classes as the number of tasks go to infinity. And so I shouldn't have incorporated this skipped. So because we do have enough time today, so I do want to talk about this. Sorry for the typo here. And here I'm going to talk about worst case upper and lower bound, and also I'm going to talk about fast rate under an analog of margin condition for compound problems. And on top of that, we also show empirical demonstration on 3 examples, which are A/B testing, opportunity loss, and firm discrimination. So maybe this is a good time to take a pause to see if there's any question. Okay, so looks like there's no question, so I can move ahead. So I will spend most of time explaining our assured star estimator. And here, just throughout the rest of the talk, I'm going to switch from the total welfare to average welfare, just to make the scaling right. So that means on top of the sum, I add a 1 over n in front of it. So then here the idea is very straightforward. We want to use our data yi and all other side information, including sigma I, to estimate this quantity for any given beta. And this will give us an empirical welfare, which we call W hat. And then we can go about maximizing the empirical welfare to get beta hat. And we deploy the selection decision by plugging in this beta hat. So the idea is that if beta hat is close to, if W hat is close to W, then beta hat should be close to the optimum. So, okay, I see a question. Can we view this problem as an integer programming problem and solve it in this alternative way? Great question. So here, if we go back to this formulation, it seems like this is an integer programming problem, but we can't solve it in this way because if we go to the statistical decision, we can see that we must restrict the complexity of this class in order to get any good statistical guarantee. So in other words, if we just treat delta I as separable 0, 1 decisions, then our complexity or VC dimension is too high. So there, we're guaranteed to have overfitting. So that's why we must use some beta to parameterize it. It doesn't have to be finite dimensional. It could be something like a smooth class or isotonic class so that we can control the complexity to be something less complex than the 2 to the n space. Yeah, but this is a great question. Okay, just going back to this. So this has a flavor to the empirical welfare maximization literature or policy learning literature. And I would say one of the key distinctions which I didn't list here, is that in that literature, often this decision or this delta I decision doesn't depend on y. But in our case, we do use the actual yi to make the decision. And also, from a technical front, we're operating in a very different asymptotic regime. So roughly speaking, if you have a discrete covariance, the EWM or policy learning is assuming a fixed number of strata and growing sample size per stratum. But in our case, we assume a growing number of strata, but a fixed sample size per stratum. So later in the talk, I'm going to talk about a case where we do have multiple samples in the stratum, but they're non-Gaussian. So there you can see a much more clear picture of how this compared to EWM. But for now, I just want to emphasize that our setting, although it looks like the EWM or policy learning, it's very different due to this compound decision nature, and also due to the fact that the yi has a non-negligible sigma I square. Okay, so one natural class of estimator that we consider is called a linearly separable estimator, where we just use the information of yi to estimate, and also zi to estimate each term here. So then our W hat, or the estimated welfare, would be the average of this individual estimators for the individual welfare. So then we know that this is just a standard, this looks like a standard empirical process problem, where let's say, suppose we can control the bias to be very small, and we can show that variance is not too big, then we know W hat is statistically indistinguishable from W, from the true welfare. So then applying some sort of empirical process theory, we can show that the deviation is small uniformly over beta. But here, there's one step which is highly non-trivial. That is, how can we develop a Fi or find an Fi such that it's approximately unbiased? So this turns out to be the most difficult question and one of the key parts in our paper. And it turns out our estimator looks like this, which involves sine and integral of sine or sinc. Well, I'm not expecting any of you to digest this, so because this looks crazy. So over the next few slides, I'm going to take a step back and show you how we go from the original problem to this estimator. And by the way, we call this estimator a sure star. So let's unpack this problem. So recall our goal here is to make this bias as small as possible. So then I just take out the definition of the individual welfare, which is the indicator of being selected times the net benefit. And on the left-hand side, we want to find a transformation of yi such that the expectation of Fiyi equals the right-hand side. So the first step of simplification is that I want to remove this subscript I, because now we're dealing I by I. So then here we can simplify this problem into the following form. And also, you can trust me that with some normalization, we can, without loss of generality, assume that k equals 0. So there's no cost, and sigma square equals 1. Right, so this is just a simple normalization or rescaling. And then we can also use the definition that y is normally distributed to expand this expectation into the CDF of the normal. So then our problem become a super standard one, or become a super simple one. That is, given a G transformation of mu, the unknown mean of the y, can we find an unbiased estimator to estimate G mu? So this is our key problem. And looking at this, we recognize that this can't be new, because this looks so standard. And there got to be some literature, got to be some famous statisticians studying this unbiasedness problem in the past. And turns out this dates back to Kolmogorov in 1950. So this is called Kolmogorov problem. And of course, there are many Kolmogorov problems, but this is one of them. So in this 1950 paper, written in Russian, Kolmogorov asked this question about whether we can find an unbiased estimate for G mu when you have a single draw, when you have several draws from Gaussian. And he showed that when we have at least two draws, then you can, and also with some actual regularity conditions on F, including that F vanishing on the tail, he's able to use a PDE approach to find this F. So in particular, he's solving his own backward equation to get to this F. And this paper, I don't think this paper has any English translation, but fortunately, thanks to AI, I'm able to understand this. And it turns out this is a remarkable paper. And for some reason, it wasn't really picked up in the history. But there's one key limitation, or there are two key limitations in this paper. One is that we need one replicate. But in our case, we only have one draw from Gaussian. So we don't have two replicates. And another limitation is that they require this G to vanish on the tail. And turns out we don't have that property. So later on, 9 years later, there's this statistician Tate wrote about using a Laplace transformation approach for this problem. And then 30 years after that, Stefanski had a paper talking about this unbiased estimation of a nonlinear function of a normal mean. And this paper introduced a Fourier transformation approach and also a polynomial expansion approach. And our paper will be based off of this Fourier transformation approach to tackle this problem. But again, this paper also assumes that the G should vanish on the tail. And this paper has some impossibility result showing that if some property of G doesn't hold, then you couldn't find unbiased estimator. But this paper doesn't include a solution when G doesn't satisfy those properties. So now let me just walk through the logic here. So we know that the expectation of a transformation of a normal mu1 can be written as the convolution between this function f and the Gaussian density. So our goal here is to find an f such that its convolution with phi equals g. So then we can take Fourier transform on both sides. And then we can invoke the convolution rule to rewrite both ends in terms of their Fourier transformations. So for the left-hand side, we have f hat times the Fourier transform of phi hat, of phi, which is e to the minus omega squared divided by 2. And on the right-hand side, we have g hat. So it seems like we're getting very close to the solution because this implies that f hat equals g hat times the e to the omega squared over 2. So then it seems like we can invoke the inverse Fourier transform to back out f, which is given by this integral. So everything looks so standard and seems like the problem has already been solved. But there are two implicit assumptions here. So one assumption is that g hat does exist. So in the standard Fourier theory, g hat only exists when it's in L1. So going beyond L1 requires more advanced analysis. And another thing is, in order to apply the inverse Fourier transform, we need this thing, g hat multiplied by e to the omega squared over 2 to be integrable. Because otherwise, this integral is not well defined. And here, in order to, first, I want to show you that actually our estimate doesn't satisfy either of these assumptions. It's pretty, and so many functions g do not satisfy. For example, if we want to estimate the at mu, that is e omega does exist, but this whole thing is not integrable, right? Because one is a constant function and it's not in L1. And in our case, and actually this phi mu case was discussed in Stefanski's paper. And in some sense, this Fourier transform approach doesn't work. And in our case, it's even worse because here our G mu is mu times the Gaussian CDF evaluated at mu minus delta. And even g hat doesn't exist because this function doesn't vanish on the tails. So as a result, it's not integrable. It's not in L1. So we couldn't really define the g hat in this case. So as a remedy, we're going to use a bit of advanced math to get to our estimator, and then we prove everything from scratch. So the remedy here is that even though we couldn't get a proper Fourier transform for some function g that is not in L1, but we can get the formal Fourier transform coming from the so-called tempered distributions. So we can still define it for many other functions. So in this case, we can actually use the rule of proper Fourier transforms to come up with a formal Fourier transform. And that deals with the first problem that g hat doesn't exist. And then to deal with the second problem that this whole thing is not integrable, then we truncate the integral range from -1 over h to 1 over h. So this is like a bandwidth or like a kernel truncation. So after you apply both techniques, then you end up with this estimator. And then you can add the subscript I, sigma I, ki back to give the welfare estimator. So it turns out that a similar idea has been studied in Penske 2016 and Zhou and Li 2019, but they have very different motivation. Okay. So this is about motivating our estimator from a Fourier truncation perspective. So let me take another pause to see if there's any question here. All right. Yeah. So we have another motivation for this particular estimator. So the strategy I just introduced can be applied to a very broad class of estimate. Sorry, now I see one question. Yeah, great question. So the question is, can you explain why the formal Fourier transform is suitable? So here, well, there are two routes to explain that. One route is that we can go into the literature, we can go into the textbook on tempered distributions, and then use the more generalized calculus to confirm this is correct. But what we are doing in the paper is sort of more convincing for people who don't have this background. So what we are doing is that we just motivate this estimator using that advanced tempered distribution notion. But then we prove that this has a nice bias property from the scratch. So later on, when I show you the bias bound, that's derived from elementary math. So we don't have to introduce more advanced stuff. But the general idea is that, well, with this improper function, just like delta function or the broader class of generalized functions, then you can at least write down an estimator, which makes sense. And then we can go back to elementary math to try to prove that this has good properties. Okay, great. So next, I'm going to introduce another motivation that also motivates our the name of the choice of the name for our estimator, a sure star. But this motivation only applies to a smaller class of estimate, but it does include everything that we study in this paper. So there's something called Stein's identity, which says that if you have a Gaussian y with mean mu and variance 1, then the expectation of y minus mu times fy equals the expectation of f prime y, where f prime is the derivative of f. So after rearranging this equality, we got mu times expectation of fy equals the expectation of y times fy minus f prime y. And this holds for any smooth f that is differentiable. So in this case, you can see that, well, the right-hand side is just a function of y. It doesn't depend on unknown mu. But in the left-hand side, we have expectation of any fy times mu. So going back to our problem, we can also re-express our g mu as mu times the expectation of fy. But our fy is non-smooth because it's the indicator function. So one way to deal with that is to smooth it. So we can choose a kernel k, and then we can replace f by the convolution between f and k. And then we apply a bandwidth on it, just like in the standard non-parametric estimation. And now this function becomes smooth. So we can apply the Stein's identity to get an estimator for this approximate quantity. It turns out if you're using the sync kernel, or what double E people call low pass filter, then we get our assured star estimator. So this is another way to motivate our estimator. And also, you can plug in some other kernels, like Gaussian kernel, and this is what we call assure CB, and CB for couple bootstrap. And we discussed this in length in our paper, but for the purpose of this talk, I'm not going to talk too much about this, because this one has a worse rate compared to the previous one. So I'm still going to focus on assure star estimator, which is given here. But now you can see there are two ways to motivate this estimator. One way is to go into the frequency domain and then apply some tricks, including using tempered distribution and doing truncation on the integral range. And another motivation is going from the Stein's identity and doing some kernel smoothing. And both will give our estimator. And going back to the question that we just got, it turns out in order to analyze the bias property of this estimator, we're going back to elementary math. So this result is obtained without resorting to any of the temporal distribution calculus. So what we show here is that if you're taking expectation of this function and you compare that with our estimate, then the bias is bounded by some constant times the magnitude of mu times h squared times e to the minus 2 over h squared. So this is exponentially small in 1 over h squared, in 1 over h. So in particular, if you set h to be 1 over square root of 2 log n, then the bias would be much smaller than 1 over root n. And this distinguishes us from the standard kernel estimation, because in the standard kernel estimation, we got polynomial rate. So there, we have to think about how to choose the best rate for h, how to do the optimal bandwidth selection. And because there, the bias and variance are both polynomial in n, in h. So then you have to balance out those two terms. But in this case, we got exponentially small rate in terms of the bias, in terms of the 1 over h. So as a result, we can simply choose h to be 1 over square root of 2 log n, and we can set this 2 for any problem we're dealing with. We don't have any parameter or the exponent to tune. So this has some connection with the so-called infinite order kernels, which was sort of thriving in 1970s. And back then, people are hoping to develop some kernels that can give you properties like this. But we're using that in an implicit way. And in particular, if we're choosing this particular choice of the bandwidth, then we can show that the overall bias for our welfare estimator is bounded by something like 1 over n log n times the average of the net benefit. So if we're assuming that all these mu i's or all these net benefits are bounded, then we get a rate 1 over n log n, which is much smaller than 1 over root n. So now you may think, is this necessary? Is it that we're not clever enough to recover a exactly unbiased estimator, or is this more or less necessary? So it turns out we show that first, actually we show that there's no exactly unbiased estimator for this problem, for this estimate, as long as we impose some mild assumptions on the tail behavior of this function. So to show this, we first show that if we can find an unbiased estimator for our final estimate, then there would also exist an unbiased estimator of the Gaussian density. And then we show that as long as a function has has a finite expectation under a normal with mean 0 and 1 plus epsilon square, then we wouldn't expect then this fy cannot be an unbiased estimator for the Gaussian density. So as a result, we show that if we impose this very mild tail assumptions on f, then we cannot find any unbiased estimator for our final estimate. So we have to use some sort of kernel smoothing to make sure that our bias is not big. But we can't make the bias exactly 0. Okay. So another thing that I promised at the beginning is that, well, let's say suppose we don't have exact Gaussianity, but rather we have microdata or individual level data. And this Y is coming off of the average of W1 through Wm, where their ID drawn from some distribution, which is potentially non-Gaussian. Then what we show is in a regime where we have, in a local asymptotic regime, where the expectation of W is mu over square root of mu, square root of m, and the variance is a constant, then we can show that our assured star estimator has a bias that looks like log n squared divided by root m plus the rate that we just got. So in other words, as m goes to infinity, then this bias also shrink to 0. And this shrink to 0 roughly at the rate of 1 over root m. And here you may think that, well, in this regime, because we can sort of get some consistency, so maybe we should also use plugin estimator by directly replace mu in the welfare function by y. But because we're in the local asymptotic regime, then this consistency is pretty weak. So then we still have like a constant bias in this case. Okay. So that's why we're choosing this local asymptotic regime. But you can also imagine choosing some other regimes that are simpler than this. And in those cases, the plugin estimator would have a vanishing bias, but the rate of convergence will be much worse than a sure estimator that does exploit this approximate Gaussianity. So the key takeaway here is that whether you're in the exact Gaussianity case or in the approximate Gaussianity case, the assured star estimator both have a better bias property. So we do want to exploit that Gaussianity or approximate Gaussianity to make the bias small. And for this one, the key technique is the Lindeberg replacement, which is a lot of fun to work with. Okay, so that's pretty much about the bias property and the motivation of our estimator. Let me take another pause to see if there's any question. Okay, so now I'm going to talk about the theoretical regret analysis for our estimator. So here to define the regret, we're comparing the optimal, like the ex post optimal welfare against our actual welfare. So here, recall that our welfare is defined as the expectation of this quantity. And we're going to we're going to deploy the beta hat, learn from optimizing the empirical welfare. So that means when we calculate this welfare, we have randomness coming from two sources. One is from the randomness of y that are initially in this function. And the second source of randomness is coming from beta hat, which is from our deployment. So we're going to use the same data y to compute and also evaluate decisions. So that's why this quantity looks a little bit more complicated. But we're going to focus on this notion of regret that is suitable for compound decision problems. So the first result we got is that if this decision class is a VC subgraph class, and we have some moment conditions, then the regret is roughly 1 over root n. So this is just a standard empirical process theory, but we do need to make some modification. So because first, we're dealing with INID data, because the data is independent but not identically distributed. So we need some modification. And the second thing is, in order to get this rate, we need to deal with the fact that vanishing variance, the variance is vanishing compared to the envelope function as h goes to 0. Because here we have both n goes to infinity and h goes to 0. So this will make the things slightly more complicated. And then we can also prove a nearly matching lower bound, which is 1 over root n. And here we only assume that mu I are bounded. And we can show that the worst case is actually achieved when all the mu i's are above ki, meaning that for everything, the net benefit is positive, or for everything, the net benefit is negative. An optimal decision here is to always select or never select. So this shows that without further assumptions, then we get this 1 over root n rate, which is kind of standard. But the next thing we're thinking about is that maybe we shouldn't consider this worst case, because this is too worst case, and it's very unrealistic in practice. Because in most practical problems, we're expecting that at least some tasks have positive benefit and some tasks have negative net benefit. So it turns out with some analog of the margin condition, we can prove a faster rate. So in this case, let's assume that there exists a global maximizer, beta star, at which the second derivative of the welfare is bounded away from 0. And also we assume that for any local maximizer, the welfare is a constant away from the global maximizer. So then under some other regularity conditions, we can show a polylog n over n regret bound. So it turns out for those who are into the margin condition and classification literature, the conditions A and B are very analogous to margin condition, which is exactly saying that, well, around the optimum, we have enough of curvature for us to make right decision. So it turns out these conditions can be satisfied when we look at the p-value thresholding rule. And there, if we're imposing the, so there, if mu I and k minus ki are not all of the same sign, and we assume there's a lower bound for the average net benefit square, then we can show that these two conditions are satisfied. But of course, this is just a sufficient condition, and we believe that this can hold for more general conditions. So with this margin condition, we can prove a 1 over n regret bound. And we can also show a matching lower bound up to log n factors. So here, roughly speaking, we show that if we restrict mu into the class that satisfies the condition for the fast rate upper bound, then the lower bound will become 1 over n. So far, we have shown two types of bound, the slow rate 1 over root n and the fast rate 1 over n. And we also prove matching lower and matching lower bound for both of them. So that's roughly a sketch of our theoretical result for the regret bound. So let me take another pause to see if there's any question about this part and also the previous part. Okay, so now I'm gonna spend the next 10 minutes each to show you 3 empirical applications. So the first one is about A/B testing or experimentation program. So here we take 331 feature A/B tests from Netflix, and this data is anonymized. And we use yi to be, we denote by yi the estimated treatment effect. And here, as you can see from this anonymized data, if we plot standard errors against treatment effect, we can get this scatter plot. And the standard p-value thresholding rule corresponds to this yellow line. And here, maybe you shouldn't take this too seriously because this data is anonymized and also perturbed by adding noises. But this roughly gives you the vibe about how tech industry is thinking about shipping a feature. So like in this case, if we ignore the fact that this treatment effects and standard errors are perturbed, then we would think that all these yellow dots would be shipped or rejected because they correspond to the case where the p-value is below 0.05. But one question that we could ask is that whether we should stick with this p-value thresholding rule if our goal is to optimize the welfare. It turns out there are 2 earlier papers that make the point that this shouldn't be the case. So one is from one of the authors of this paper, Tim Shudijono, who work with the Netflix people, showing that if you want to maximize the overall welfare, then you should experiment more. And the key observation is coming from this histogram, where they found that the treatment effect estimates tend to be very heavy-tailed. So if that's the case, that means experimenting more can give you more likelihoods to get to the tail of the treatment effect. So then it will be more likely to ship something that is substantive. So in this case, we want to reevaluate this problem using our Assure estimator. And it turns out we first need to define our thresholding rule or decision class. So here we keep the p-value thresholding rule. And as I mentioned before, because this beta does, you can take beta to be 1.96. So that means we can always, we never, we never do worse than the standard thresholding rule that was, that has this beta equals 1.96. So that's our decision class. And then we need to think about how to calibrate our cost. So of course, the cost for running A/B test is pretty complicated. That involves the engineering cost. That also involves the cost of like developing this feature and debating with other teams, and also thinking about whether this feature actually makes sense, and going through the legal team to see if this feature is allowable, things like that. So it's pretty hard to get a measure for that. So here, what we are doing is that we just benchmark or calibrate this cost based on the median treatment effect. So we just look at all 331 treatment effect, and then we take their median, and we set our KI to be a multiplier times this median treatment effect. So then here we give 5 different curves. So the black curve correspond to no cost. So imagine a world that we don't have any cost at all. Then we can get a welfare curve that looks like this. So in this case, you can see the peak roughly happened at 0, meaning that instead of thresholding the p-value at 0.05, we should really threshold the p-value at 0.5 because there's no cost. And in that case, we should just experiment as much as possible. And we just keep the ones that has p-value or that has the treatment effect estimate, which are positive. Right? So as long as it shows a positive signal, then we should do it because there's no cost. But of course, in practice, the cost is never 0, and often the cost can be substantial. So here, as you can see, once we increase the multiplier for the median treatment effect, then this curve is tilting more and more towards the right. And another exercise we're doing is that we want to see for which choice of the multiplier can we justify the 1.96 choice in practice. And this is the yellow curve in the right panel. And here, we just plot a sure star optimal threshold against the cost multiplier kappa. And we see that roughly speaking, 1.96 can be made sense of when the cost is twice of the median treatment effect. So I think this is another benefit of our assured star estimator, which is that we can rationalize our existing choice or status quo choice by reverse engineering the cost. So then, even though the engineers or data scientists cannot really come up with a good cost measure, but we can try to reason about whether they think the cost is below or above twice of the median treatment effect in order to justify whether we should relax the criterion or strengthen the criterion. So I think this is another way of using a sure star that can be super effective in practice. So the second example is the opportunity atlas or creating moves to opportunity experiment. So here we have 13,600 census tract, and YI is the average children income ranks given Black and or basically is the average income ranks given that this person is growing up in a Black family with parent income at the bottom 25% percentile of the income distribution. So here we try a bunch of methods and we compare their welfare. And the method we include closed Gauss, which is from Kevin Chen's job market paper. And also we try a few variants of closed Gauss. And we try some other methods like Fay-Harriet, which is essentially adding the covariate part onto the thresholding rule. And we also try empirical Bayes linear shrinkage and the naive plugging. And we also try like the standard thresholding T statistics without adding the covariates. And just to show you the results, I'm going to focus on the right panel. And here I'm going to normalize the welfare measure to be 0 for the naive rule and to be 1 for the Fay-Harriet rule. And we can see that whenever we work with Assure, we have a lot higher welfare. So like, for example, this 2 means is like, so given naive being 0, this is roughly twice as good as Fay Harriet in terms of the gap between the welfare of this method versus the welfare of the naive. So we can see that at least in this semi-synthetic data exercise, we can achieve a lot higher welfare. And the last application is this resume correspondence experiment from Klein et al. Paper in 2022. So here we have data from 108 firms and roughly 1,000 job applications per firm. And YI is the callback rate gap. And we follow their paper to model YI as a normal random variable using the central limit theorem to get sigma I squared. And then we consider a linear shrinkage rule that uses a Gaussian prior with an unknown mean at 0 and unknown variance as 0 squared. And then we can show that the thresholding rule can be written as a one parameter family, even though we have two parameters in the prior. So it turns out like here, the M0 and S0 squared will collapse into a single dimensional parameter beta. And now we're going to work with this decision rule class. And then we calibrate our cost to be 0.025 to match the number of rejected firms in their paper. And you can find more details in the paper. And once we have the cost and decision rule class, we can apply Assure and also the plugin estimator. And we can see that here, Assure rejects or call out more firms than what plugin is suggesting. Because here, the blue curve gives the boundary, decision boundary for the plugin, and the yellow curve gives you the decision boundary for Assure. And we also compare our method with the non-parametric empirical Bayes estimates in their paper. And we found something really interesting for this particular application. So here, all the ones that are circled by these black circles are rejected by the non-parametric AB estimate. So as you can imagine, their decision boundary is roughly this, although their non-parametric estimates are a lot more complicated. But here, one weird thing is that using this non-parametric AB, they reject this firm that has nearly zero callback rate gap, meaning that at least on average, across all positions, they're doing pretty well. But the reason this one is picked is because sigma I is pretty large for this firm. So in other words, non-parametric Bayes seems to penalize a lot more on the sigma, on the variability of this measure compared to Assure star. And I would say, in this case, maybe penalizing this firm too much is not very good, given that this firm already achieves a near zero mean. Okay, so that's pretty much about this Assure star project. So I think we still have like 2 minutes. So I want to quickly go over another one that has to do with the binomial means, and which is a joint work with Yan Chen from Duke. And after that, I will wrap up and start taking questions. So one thing you can see from the resume correspondence experiment is that we're using Gaussian approximation. So if you look at firms, because each firm has 1,000 applications, so maybe this Gaussian approximation makes sense. However, if you dig deeper into this data set, we found that for each firm, they roughly have 125 jobs. And for each job, there are roughly 8 job applications, with roughly 4 with white sounding names and 4 with black sounding names. And if our goal is to get a discrimination measure for the job level discrimination, then it seems like the normal approximation is not going to be a good choice. Because in this case, for each group, we have a binomial with n equals 4. And so this is not really Gaussian, and it's neither Poisson. And another thing is, in the previous work, people are trying to apply empirical Bayes onto the binomials directly. But they do require the size of the group to be homogeneous. But in this case, well, while most jobs have 4 four applications in each group, but there are some jobs that has a 3 or 2 applications. So there it's unclear how to work with that. And even computationally, it's pretty hard to come up with a computationally efficient prior with heterogeneous Ni, or Ni1, Ni2, which are the sample sizes in 2 groups. So in other words, like even you are a subjective Bayesian, it's pretty hard to give a conjugate prior for N. So in this case, it's unclear what's the right Bayesian estimator to use. And another thing is, when we go into the lower level, like job level discrimination measures, we do want to maintain some reporting consistency, meaning that the average of job level measure should equal to the firm level measure, because otherwise the discrepancy can be very hard to make sense of. And lastly, it's unclear how to incorporate covariate or side information in this framework. So motivated by this, now we're thinking about compound estimation of binomial means, where instead of looking at our welfare, we're looking at the mean square error. So in this case, we can first consider a class of estimators that look like a weighted average of Y bar, the global mean across the firm, and the YA bar, like the local mean across the jobs, and also some covariant information. So under this class of estimators, we can ensure reporting consistency, meaning that the average of this class of estimators, the average of this estimator across all jobs will recover exactly the firm level discrimination measure. So then we can look at the mean square error. Sorry, I missed a expectation here. And we can see that this can be written as something that is easily estimable minus the sum of the job level true discrimination times the expectation of our estimator. So this looks like the Schur estimator I showed you before, Schur's identity I showed you before, because our goal is to find an unbiased estimator for the expectation of some function of our data multiplied by the true mean. So in order to do this, we develop an approximate Schur that looks like this. Again, I'm not expecting any of you to digest this. It looks very complicated, but we have a way to go from the first principle to come here. So that's how we derive this. But the general idea is that for this class of functions, we can find an exactly unbiased estimator that looks like this. And then we can apply this estimator to the problem we just studied and get job level discrimination measures. So with that, I want to conclude the talk. So in this talk, we introduced these compound selection problems, and we argue that this is very common in economics and also in many other areas. And in our Assure framework, we mainly highlight 3 different big points. One is that the standard estimate and select pipeline might be inefficient. So like in the standard pipeline, people often are trying to estimate the parameters and then make decisions based off of that. But we're saying that, well, maybe we should directly optimize the welfare, and we show you a way to make this optimization statistically sound. And the second thing is, well, because we have heterogeneous tasks or populations, so then people often impose a Bayesian assumption on it, and then look at the Bayesian welfare. But the Bayesian welfare depends on a correctly specified prior. So in other words, the interpretation of that welfare will be averaging over a hypothetical population. And this will be suboptimal when there's distribution shift or when there are there doesn't exist a true population behind it. So instead, we're just targeting the sample in the problem. And lastly, we're saying instead of looking for the global minimum, like the globally optimal policy, let's look at a restricted decision class for both interpretability and flexibility. And our tool allows us to control the complexity of that and then make our optimized decisions good enough. And the bottom line for this talk is that you can actually view Assure as a decision theoretic approach for empirical bias in a compound decision problem. Because here we're not estimating the hyperparameters using MLE, we're using our welfare estimates to optimize the to optimize the hyperparameters. So I think this decision theoretic approach might be more disciplined than the standard estimation-based approach for empirical bias. So with that, I'm gonna stop here. Thank you.
All right, thank you very much, Dr. Lei, for the insightful talk. So now let's stop recording, and we will open the floor for questions.